In this video, I will show you how you can model and solve a knapsack problem using Python and Gurobi optimizer. This video was created using Anaconda Python distribution and Gurobi optimizer. These are the instructions if you want to install them yourself. You need also a license for Gurobi, either free evaluation or paid or a free academic license. This video was created using Anaconda version 2019-07 with Python 3.7 and Gurobi optimizer version 8.1.1. So the knapsack problem, in the knapsack problem we are given n items. Each item has a profit pi and weight wi, and I will be indexing items from 0 to some n minus 1. This is just so that we are consistent with the Python code. And then we are also given a knapsack capacity C. And the problem is we want to select a subset of items such that we maximize the total of the profits pi of those selected items. And at the same time, we do not exceed the total weight. That total weight doesn't exceed the value C. So how can we write this problem mathematically? So here we just have a code that shows us some imports. I'm importing pandas and NumPy, and then importing the Gurobi library. And here is the example data. A knapsack has capacity 9. Profits are listed here. So there is actually a total of 7 items with these profits and these weights. And we want to select a subset of them such that we don't exceed the capacity 9 and we maximize the profit of selected items. Here are some examples, example applications. So you can think about a mountaineer that is packing a knapsack, wants to take a set of items with the highest possible value, but at the same time doesn't want to exceed the total weight of the knapsack because he wouldn't be able to carry it. Another problem is an investment problem. In this case, this is a simple investment where we're not concerned with the risk, but we just need to select a subset of investments, each of them for a fixed amount, WI, such that we don't exceed our budget, but yet also make the highest possible total return from our budget. And then airline cargo, a similar problem where we maximize the profit or the revenue from the served orders, but at the same time each order has a weight or request has a weight, and then we don't want to exceed the capacity that the plane can carry. So to model this problem mathematically, we can start a new cell here, and we can change it to Markdown. And this is the feature of Jupyter Notebook or Jupyter Lab, where we can actually edit, we can put a code. So for example, to put a heading, I'm going to put mathematical model for the knapsack problem. And if you press Control Enter, you will see that it compiles as a heading. And then, for example, I can start defining. If you double click on it again, you start editing. And what I will define is, well, we need to define decision variables in the optimization in such a way that we allow all possible solutions for the knapsack problem. So if you look at those items, we need to be able to select item 1 or not select it, and select item 2 or not select, right? And so if we could define decision variables, we could define them decision variables as xi equal 1 if item I is selected, and otherwise equals 0. So equals 0 otherwise, right? And that we need for I equals 0 to n minus 1. So actually, what you saw me typing, you see, resulted in this text. And actually, I'm using the Jupyter Notebook markup language or markdown language. And it actually is a mix of different things. It has a bit of HTML, a bit of LaTeX, and a bit of other things. So for example, this format is actually taken from LaTeX equations. If you want to know how to write these, just search for LaTeX equations. This is the simplest way, where we insert symbols inside a text. You just start your mathematical symbols with $, and end them with $, and then inside you have to use a certain relatively simple language to express symbols. So for example, underscore means the next thing will be an index. If you have two indices, you have to enclose them in curly brackets and so on, right? So what I did here results in this, right? So we define decision variables. Now we can write the objective. So the next line will be the objective. In the objective, we want to maximize the sum of profits of items we selected. So we will say sum, and then the sum will go from I equals 0 up to n minus 1, right? And then the sum will be, what will it be? Adding. It will take profit for item I, multiply it by the variable, decision variable for item I. We can actually comment this as total profit. Right, so what I did right here calculates for me a total profit of the subset of items that is selected. And notice how this works. If xi is equal to 1, then we have the item selected, and then the profit will be here multiplied for this corresponding item, will be multiplied by 1, so it will enter the sum, and it will actually add up to the total profit, And if the variable is 0, that means we're not selecting the item, and then the profit is not going to enter the sum, so it's going to be excluded from the summation. It's not going to increase the sum here for us. Now we need also constraints. So I'm going to write, as it is in mathematical programming, typically written subject to what are the constraints. And the constraint, there is really one major constraint. We need to make sure that the sum, again, the same sum. So actually, I can reuse this and then modify it slightly. Sum for I equals 0 to n minus 1. But this time we want to calculate the total weight of selected items. So I'm going to change P to W, Pi to Wi. And then I need to say less than or equal to C. And this, we can again put a comment total weight, right? And so this constraint, in a very similar fashion as the objective, this constraint, the left-hand side of it, calculates the total weight of items that are selected. If there is 1, the weight is multiplied by 1. If there is 0, weight is multiplied by 0. So the sum will actually add up all the weights of all the selected items. And the constraint says, well, this sum of weights cannot exceed capacity of the knapsack C. We also need to add one more constraint, which is saying that the domain of the decision variables must be in 0, 1, or you could say binary, right? And we need to say that this is for, actually the same for as here, for I equals 0 to n minus 1, right? So this says the variables are binary, they can only be 0 or 1. And this is actually complete model. So now how do we solve this using Python and Gurobi library in it? So I'm going to again create another cell here. You can create it by pressing B or by clicking this plus button. Then you can start editing by clicking the mouse on it or pressing enter. And we will actually start implementing this model, mathematical model that is written here above using Python and Gurobi library. And I will do this by step by step, first implementing it and compiling parts of it, and then we will put it all in a function that will kind of encapsulate our model so it can be reused later on. So we'll start, first of all, there is a number that is not given here above, but was part of the model, which is n. N is the number of items. I didn't give it because it can be derived as length of p. And in fact, right, so the length of p in this case, it's 7, right? This is the number of items, but it's actually the same as the length of w. So if I'm given the data as 2 vectors, I should probably make sure that they are the same length. So I am going to, right, let's see, run this. Control Enter runs the cell, or you can click play here. So this displays the value of n equals 7. And actually, I'm going to, again, calculate length of w. And I'm going to use the Python command assert that n equals length of w, right? And let's put a comment here. P, or length of p and w should be the same, right? And if we run this, this is not going to display anything, but suppose in the data we made a mistake and we put another, let's say, weight here, and then we run this, and this gives us an error, right? So we have a warning that something is wrong with the data, right? Let's undo this change, run it again, run this again, right? This is good practice, actually, if you know something about the data that the user could potentially make a mistake in the data, then it's a good idea to put these assertions and check your model, check the data before you start creating your model. So then we have all the data, and I'm going to create a model in Gurobi. In Gurobi, often you have, in Gurobi examples, often M is used as an object of the model. However, M is sometimes in mathematical programming also another symbol for a number of resources or something else. Therefore, I'm going to use the variable name model for the Gurobi model. Now, we have imported Gurobi library into the main namespace here, right? So we can just use model, but of course, this is the model from the Gurobi PY library. So this creates the model. Let's actually try and compile this. And you see I have an academic license. I will also use a parameter, which is a good idea, log to console. And I'm going to set it for now true. This is the parameter that decides whether the Gurobi is going to display something for us on the screen in the Jupyter notebook as a log, or it will work quietly. If you set this to false, we may work quietly. And then I will also use time limit, and I'm going to set it to, let's say, 60. This is in seconds. Again, it's a good practice to set it if you have a very large model and might be solving too long. It's better to set a limit to start with. You can increase it later. So the model itself, we need to add the decision variable. So we're going to follow exactly what is said here. We need decision variables xi for I equals 0 to n minus 1. So we need n decision variables. And those decision variables we can add by saying x equals model add vars. And then, so right, if you want one variable, like if you wanted x0 only or x1, x2, you could use add var. We want to add all of them at the same time. Therefore, I'm using add vars. This adds multiple variables. And because I know this function, I know you can specify how many decision variables you want, right? Index 0 to n minus 1. And I also want to specify variable type. And this is the parameter vtype. I'm going to use positional reference to parameter. Vtype equals grb.binary, right? So if you actually don't know, let's try to compile this, right? So that actually started displaying some parameters, some output, some log, and there's no error, so this works. If I want to find out more about, what are the parameters of add vars in the model, you can actually go to Gurobi documentation. So in Gurobi documentation, you will find it at gurobi.com/. documentation. And if you go there, you can, it's a good idea if you're using Python, Gurobi with Python, to select here Python just to limit all the examples and all the specification to just Python libraries. You can see you can access Gurobi from other languages. And then we can go, for example, for reference manual, and we can click on Python API details. And then you can find in the model, you can find the function add variables. Where is it? Add vars here, right? So if I click, for example, add var, I will find out what the parameters of adding variable is. You can see, you can set the lower bound of the variable, upper bound. These are the default values, 0 and infinity. Another constant, GRB infinity. You can set the objective coefficient, and here is the V type, right? The default is continuous, but you can, of course, change it. There is GRB integer, or these are the values. GRB continuous, GRB binary, GRB integer. There's also something called semi-continuous and semi-integer, right? So you can find out about parameters, and if we go back, we can see parameters of add vars, we can see add constraints, one constraint or multiple constraints, and you can see, right, how do you add multiple variables, and how do you add constraints and other things. So you can learn more about the documentation from this website, or there are also PDF documents. So going back to our model, we added the variables. I compiled this with Control-Enter or by pressing here play, and this clearly doesn't give me an error. So it looks like it's working correctly, and that's a good idea. Always build the model incrementally, run it and see if it is raising any errors. If you try to write 10, 20, 50 lines all together and you don't have a lot of experience, then you're very likely to make a lot of errors, and then debugging, finding those errors was going to be very difficult. So after we added the variables, this is the only type of variable that we have in this model. We will say model set objective to add the objective. So we move from the variables to the objective function. So the objective is a summation of all the profits multiplied by the variables. So I could, normally summations in Python are done using the sum function. However, Gurobi has created a faster version of sum for creating expressions using variables and parameters. And the function is called quick sum. Again, it's part of the Gurobi Python library. So be careful. You can only use it if you imported Gurobi Py into the main namespace. And this quick sum, what does it say? It should say pi, right? We need to refer to this as 11 from the list, multiplied times xi, right? And this we need to specify. This is for what is I? I is in range n, right? And one more thing, just before the last closing parenthesis, we need to specify that this objective is of type maximize, right? Maximize, GRB maximize. Obviously, there is another version of this parameter. It's called minimize, GRB minimize. This is, we specify that this summation, we want as high value as possible. Again, compiling it will give us, right, an output that doesn't show any errors. So that's good, right? The next thing we need to specify is constraint. So this is, in this case, it's just one constraint. So we're going to use model add constr, right? If you had multiple constraints, there would be s. But this is just one constraint. And actually, again, since it is the same summation, right? This is the same sum. I can actually copy and paste it and just change that. In this case, I'm not summing p times x. I'm summing w times x, right? And notice, okay, this, if I try to compile this, for example, this is going to raise an error. Actually, this is not an obvious error. You can't really guess what Gurobi or Python mean here. But what we forgot actually is we forgot to define the other parameters of the constraint, right? We should say that the sum is actually less than or equal c. That's what we missed. So before the last closing parenthesis, we should have said less than or equal C, and then compiling this doesn't give us an error anymore. Actually, it returns Gurobi constraint object, right? This is the feature of Python that always returns prints the last value returned by the last command. So we added a constraint. There is no error anymore. And then what we can do in this case, well, we should still, we see still here a line, xi is binary, but actually when we added the variables, we've already defined this domain binary. So we don't need to add anything here anymore, right? All we can do is now to call model optimize, right? So if we call model optimize, let's just open it like now, and then run, and you will see that actually Gurobi runs optimization here. And at the end, very quickly, this is a very simple model and a very small data. It returns optimal solution found. Tolerance is very small here. That is set by default. Best objective is 1.5 e plus 1, which means it is 15. And the best bound, the highest possible value that can be achieved, is also 15. So that means this is an optimal solution. The gap between, the difference between those is called a gap, and the gap is 0, which means that we have found optimal solution, an optimal solution, right? So it would be also nice to see what are the items that were now selected. So what we can do is we can say something like for I in range n, let's check if an item is selected, right? How do we do this? We can check it by checking parameter or attribute x of variables. So what we do is, for example, we could say if x I, variable I, if its attribute x, which returns the value of the variable, if it is 1, then this is the selected item. If it is 0, then it is not selected. Now, you might be tempted to just say equals 1. However, this is not a good practice because, you know, so the solver actually returns values which might be, these are floating point values, which might actually be slightly off, slightly above or slightly below 1. So, for example, it might be that the actual value of x is 1.000017, something like this. It is effectively 1, but of course, mathematically speaking, it's not equal to 1. It is slightly more, right? And the same thing, you know, could be 0.99999, something like this, and it's also effectively 1, right? So same thing for 0. Instead of returning 0, the solver can actually return something like this, right? Or, so it's safer, instead of comparing this to an actual exact value, we can simply say something like if it is 0.5, okay, then it's 0.5, then this is the selected item, right? So we could say print item, and we could say I is selected, right? And we could run this. And you will see item 0 and item 3 are selected. We didn't print the non-selected one, so we can actually verify 0 is this item, weight 2, and 3 is this item, weight 7. You see the total weight is 9, so actually use the capacity of the knapsack. And then we selected profit 6 and 9, so the total profit is actually 15, and you can see this is actually correct. The best objective value is 15, right? Now, this is just running this model once, but it's a good practice to enclose a model into a function and be able to reuse it. So since this is now working, I tested it, what I will do is I will define a function. Let's call this model KP, model knapsack, right? KP from knapsack. And I will give it parameters C, P, and W. Right, which is the data of the knapsack for which I want to solve. And then we're going to select this and press Tab to indent this. And then what I will do is, rather than print, I'm going to return the solution. So I will say, for example, well, I will define something called items selected, right? And this will be a list, and I could say, right, if an item is selected, then let me add it, append I, right? So what we do here is once the problem is optimized, we say, well, let's have an empty list of items selected, and then let's go, and for every item for which the variable value is 1, let's append it to items selected. And this is, of course, append, right? And then we can return items selected, right? So this will actually work. There's actually an even shorter way, right? So if I compile this, first of all, it doesn't display anything, right? And there is no error, so looks like I didn't make any mistake. But now I can do is I can say model KP and provide it with this data C, P, and W. And if you run it, right, it runs the actual function, it solves it as before, and actually you see as an output, it displays what this function returns, and this function returns the item selected, 0, 3, right? So I could, for example, assign items selected equals, right? And then I could do something like print and say items selected are, and then right, and run this, and then you would have the comment here, right? So this works. However, actually, you can make this much shorter. This kind of incremental building of an array can be done with one line. We can basically say, let's create items selected as an array of I, put an index I, for I in range n, so you see the loop is now here inside, and then add the condition to the loop if xi x attribute x is more than 0.5, right? And that actually replaces this whole, right? With one line, I remove these 3 lines, and this should also work, and I could even replace this in place of this. Right, so I'm going to keep it as it is now, and again run this and test this. And let's try actually to add one more parameter. I'm going to add here log to console, right, and make it the default true. And instead of showing here true, I will put log to console here. And then let's add another parameter, time limit equals, let's say, 60. And again, change this 60 to time limit, right? And so, for example, now I can control, I can say, don't display it. Log to console equals false, and then run this. Oops, I need to recompile this again, and then, right? And then you see it is now solving the problem, but not displaying anything. Just this print is showing anything because I changed log to console parameter to false. Another thing we might want to get is the objective value. Objective value is another attribute. So again, if you want to consult documentation, we can go to Gurobi documentation as before and find attributes. So if we click attributes here, you will see there's a lot of attributes, and they are divided into model attributes and other variable attributes, constraint attributes, and so on. So what we, for example, used so far was a variable attribute x. You see, these are variable attributes, and x is an attribute that returns the value in the current solution, in this case, the optimal solution. We can also find model attributes, right? So model attributes, for example, has number of variables, number of constraints, and a lot of other things, right, which we can query. And one of the things we can query is objective value. So we can actually check the value of the current solution, right? So if I go back and say int, or let's say total profit equals, and I could say model, and then get objective value attribute, and let's actually turn it into an integer, and and then return, instead of item selected, I return item selected and total profit, right? And then I can say here, when I catch the result, I catch also the total profit. Item selected are, right? And the total profit is, and I could say total profit. So let's make sure we actually run this cell and then run this cell, and you see it now displays what we expect. 15 is the profit, and these are the items selected. So what's the advantage of defining it this way? Well, if I have this model, I can now solve this problem for any data set, right? So suppose I have another data set. Let's say I'm going to generate it randomly. So I'm going to import from random package, import rand int, and then I will say, well, let's generate an instance with c equal 1000, and let's say weights will be rand int 5 to 10 multiplied by 21. Let's say I generate them like this for I in range 0 to 100. It's actually range 100. This is the weights, and let's say I generate profits in a similar way. However, the profits will be, let's say, from 100 to 120, right? And multiplied by weights. So there is some correlation between profits and weights. And again, for I in range 100, right? If you generate this, there's one more thing here. If I generate this, then the data will be different every time. So for example, if you generate it the first time and print the profits, this will be the profits. You generate it again, there will be different profits. And again, there are different profits. If I want to always generate the same numbers, with random number generators, you need to set the seed. So I also need to import the seed. And I want to say, well, let's fix the seed to something like a number, let's say 124. And then if you generate profits and generate them again and generate them again, every time I generate them, they are the same, right? So now I can actually solve the model. So this is a new data, CWP. If I call the same code again for this data, then I am actually going to solve a different knapsack problem, right? I am solving now a new knapsack with 100 items, with these weights and these profits, and this using the same model as before for different data. I find a solution very quickly. We could actually see the log if it is working, right? So the way it is working, it is solving something, giving me a solution, and then says, oh, the gap is 0. This is actually an optimal solution. And you see, let me hide the log now, and you will see that items selected are, there's 6 items that were selected as the optimal solution, and the total profit is now 118,083. Right? So I can solve with in this way the knapsack problem for any data. If I need it in the future, I can just reuse this function, remembering what the data is, what C, P, and W means.